Today, we are talking with Freddy Alcazar. Freddy is an electrical engineer who works for INEO. He is currently the Senior Technical Proposal Business Development Manager, and he is mainly responsible for developing markets and high-power HP generation technologies. He is our expert on the grid stabilization plan, a trend that is rapidly spreading around the world. Due to the effects of incorporating, among other things, renewables into the grid, disorderly growth, and instabilities in generation systems. So, this stabilization proposal helps to provide security and reliability to the grid. Freddie, we had him in Puerto Rico a few days ago, where he shared this presentation with us that we are going to repeat because it was such a precise and clear presentation that it's worth reviewing it at a calmer pace and sharing it more broadly. Freddie, it's a pleasure to have you. I greatly appreciate that you took the time to give us this opportunity. So we're all ears.
Very well. Let me share my screen. Let me know if you can see it.
Yes, we can see it.
Perfect. Well, hello. Hello. My name is Fred Alcazar, and the idea here is, as Johan mentioned, to present a bit about power, what we do to help stabilize the grid system. As he said, this presentation is based on one we gave in Puerto Rico. The introduction isn't really necessary, but it's there if anyone needs it. The agenda for this discussion is the same, with three main points. First, an overview of our solutions. Then we want to talk a little about the microgrid controller, and finally, Genbacher solutions. What real-world examples are there of this? First, the general description of the solutions. Well, one of the most important points when we are talking about helping the electrical system is to comply with the conditions imposed in the grid codes in order to connect to them. For this, the first thing we want to discuss is the technical capabilities for complying with grid codes. The first point is, in general, the fact that we have many years of experience working on this. This includes interconnections to grids in different countries, certifications, preparing our controller, testing, and we bring all of this as part of our solution to any units you purchase or any plants you install. Here, in this particular part, we are showing how our simulation models work, an example of the simulation versus a real test. You can see that the model is very well made. It is based on real tests. The idea is to give the client peace of mind that when it comes to connecting to a system, whether in Puerto Rico or anywhere else, Genbacher can support you thanks to the experience we have. It has definitely been more than 15 years that we have been involved in network code connection topics. Second point regarding technical capabilities, which is the frequency control part. As you know, the frequency depends on the relationship between what is generated and what is consumed. And our solutions, our units in particular, are very good at providing frequency control services because we have fast response times and are very precise with our operating points. The response times are very fast. Our operating ramp rates are very fast. And these are key factors to help with frequency control. Then there's the part about reactive power management. Many of you will know what reactive power is. For those who don't, this figure helps a lot. Here we have a good example, something many of us know, a beer. The real power, which is kilowatts, would be our beer, and the reactive power, which is measured in kvar, would be the foam. It's not very useful, but it's there. And the total power, the apparent power, is the sum of both active and reactive power. It's not a direct sum, but the idea is to understand that reactive energy is part of it. Why is it important? To support the electrical system. We are mainly talking about the voltage aspect. Thanks to our standard design, from minus 0.95 underexcited to plus 0.8 overexcited for all generators. We can greatly help absorb and produce reactive power, positively impacting voltage control by raising or lowering it. And we also have a fairly quick dynamic response capability. All of this helps with the stability of the system. And the last point within the compliance of the grid code is the fault part, the fault ride through. This means a requirement that is being seen anywhere in the world. Initially became important because when you have a lot of distributed generation and there is a small voltage dip or short circuit in the system, the units have to keep operating. Network codes have evolved, and today it is a requirement that all units, regardless of their technology, can withstand or remain connected during a voltage dip. This example I'm showing you here is what is called LVR, low voltage ride through. Low voltage. Our units can withstand drops of 30% to 0% for up to 250 milliseconds, which is normally the maximum time that is set by grid codes. We can demonstrate all of this not only through simulations that can be provided to assist in the connection system or the connection process. We can also guarantee it because we have conducted numerous tests ourselves by creating real short circuits and observing how the units continue to operate. And from there, I would like to jump to the second part of our technical capabilities, which are now the ones that might be of more interest to you as operators. First is the quick start part. Our units normally have a synchronization time of less than 1 minute and can achieve synchronization times of only 30 seconds. It should be noted that this is not for all units. Certain models may have this capability, but this ability to synchronize from the start signal to grid synchronization in 30 seconds can be extremely helpful, especially when looking to provide frequency control services. Due to our fast start and ramp rates, we are ideal for balancing operation and for peaking operation. Peaking basically means that a plant connects only to sell at certain times of the day when, for example, energy prices are high, or at times when there is a need for energy that renewables do not normally cover. And another reason why this is crucial, is that we can very easily smooth frequency fluctuations and quickly respond to changes in demand. The figure I am showing here illustrates the different ramp types our units have, from super fast start to standard start, ranging from 100 seconds to reach full load to 300 seconds to reach full load, meaning 100% power. Then there's the flexibility aspect. What do we mean by flexibility? Well, the most important point for this type of operation is the possibility of having multiple starts within a single day. It's not a problem to operate for a while, shut down the unit, and then restart it. Start the unit, connect it, and continue producing energy. This is something that can be done. Another point is that our units also come ready to use hydrogen as a fuel. You might say it's not necessary, but we have seen a global market need to be able to use hydrogen as a fuel, and all our units can do so with up to 25% hydrogen. We also have units that can run on up to 100% hydrogen. Of course, that will depend on the exact model and the power you need. Then there's the adaptability aspect. Adaptability means we offer more than baseload power. We can also provide ancillary services like frequency and voltage control, inertia, and even participate in balancing markets. Normally, this means that a certain amount of energy is sold and the plant is prepared to deliver it. And here, for this adaptability part, the key capabilities of our units are fast ramping, responding to demand changes via external or automatic signals depending on the function, and reacting to external signals. Basically, We can prepare our unit for any type of interface, depending on your needs and what you have in your system. And finally, there's modularity and scalability. This part is quite important. As you know, our units are offered from 250 kW to 10.5 megawatts. Many of them, in fact, up to 4.5 million. An important point here is that a plant of, say, 100 megawatts could be made up of multiple units. This gives you the possibility that if, for example, one of the units fails, the rest of them continue to operate and power continues to be delivered. Another point is that if you want to increase the size of the plant, it is quite easy, when there is available space, to add more units depending on the layout. Remember that we not only have options for units installed in rooms, we also have containerized units. Then there's high efficiency that is maintained at partial loads. What does that mean? Remember that for engines, the highest efficiency is found when we are at maximum power. If a plant has, say, 100 megawatts, a 50 megawatt partial load can be met by units running at 100%. This means the plant is at 50% capacity, but the units themselves are not. Therefore, there is lower gas consumption and higher efficiency. And once again, the modular design enables scalable implementation and expandable capacity. These are truly very important things that must be taken into account. Then, speaking a bit about the ancillary services we can provide, first is frequency support. I think this part is quite obvious. We can deliver active power or lower the level of active power to help maintain the frequency. Here, the super fast start is very important, especially when selling energy for this type of operation. And the other point is that it can be activated automatically through operator commands, which means that there are a series of functions that our system can have where, depending on the frequency deviation, there can be an increase in power, a decrease in power, without having to wait for the operator's signal. This depends on how this service is offered. Then there's the voltage support part. Here, as we said before, we can provide voltage control through the wide reactive power capacity that our units have. Remember that a plant composed of multiple units implies that all these units can increase the amount of reactive power delivered or can start consuming reactive power according to the system's needs. There's also the fact that we could potentially operate as a synchronous condenser. A synchronous condenser is basically the generator operating without the engine, and it can deliver reactive power when, for example, you want to save gas. It is a type of operation that may be of interest depending on the need that the grid operator may have. Then there is the part of inertia provision. Well, inertia, as you can imagine, is what provides the network with quite a bit of stability. The more inertia a system has, the fewer problems with high frequency deviations will occur. Since we use synchronous technology, synchronous generators, we are normally delivering inertia to the system. Therefore, the system will be interested in having this type of technology connected. Finally, black start capability. Black start means that in the event of a total system collapse, as we saw in Spain this year, the plants with our units can begin the black start process. Black start requires just a little bit of power for the auxiliaries, which can normally be provided through, let's say, a small diesel engine. But then by supplying energy to the auxiliaries, our units can start, and little by little, through standard methods today, we can begin to help energize the system energize buses, energize transformers, and then energize lines and allow the connection of loads to the system. Normally, it is a service that a grid operator considers important and can pay for additionally. Now, after having shown you the capabilities our units have to support the electrical system when we are connected in parallel with the grid, we also have the possibility to provide or sell a microgrid controller. That may be more interesting in cases where the power system does not exist or has many problems. Well, let's start first with what a microgrid is. It is a small power distribution system that has multiple distributed energy resources, has loads, and also includes storage systems. Here on the right, the image shows roughly what the microgrid would look like. It may or may not be connected to the utility grid. And within the microgrid, you will find different primary generation sources, such as gas and diesel engines, renewables and batteries, as well as loads like electric vehicles, commercial, industrial, and residential loads. The typical size of a microgrid ranges from 100 kilowatts to 10 megawatts, but of course there can be much larger ones. We do not limit the size of the microgrid with our units. And the main point of a microgrid is resilience and providing an alternative to the public grid. How does our solution work? Our solution works with two parts: what happens in the cloud and what happens on site. As part of our master controller, we offer this subfunction, the microgrid function, which can help manage the different distributed energy resources, thus, depending on what is happening. For example, if there is no grid connection and there is PV, there are batteries and engines. As long as there is, for example, enough solar energy, the microgrid system would ramp down the engines and use only the PV system and the batteries. And depending on how conditions change, it commands engine starts and controls the system. Basically, it optimizes how the energy solutions are used. At the end of the day, the idea is to maintain both frequency and voltage in this islanded mode, keeping them within limits so that the units, loads, or people connected there do not experience any problems. And another point is that we can also offer black start capability in case there's an interruption. Once again, through our units. This is what happens at the level of the plant where the microgrid is located. The second part is the cloud. In the cloud, we can manage, as I said, all the different DOS. We can understand specific plant requirements. We can receive weather forecast information, market data such as the cost of energy if we are connected to the grid, the cost of gas, etc. And we can seek to optimize the use of everything within the microgrid so that there is always minimal expenditure. The aim is to improve both operational efficiency and the overall balance of the system. That's what our microgrid controller solution offers. Benefits. There are many benefits to using our microgrid controller versus another controller here. I really like this slide because even though it has a lot of information, one takeaway is that, in general, things like renewables integration, state of charge control and battery storage management, management of the different DRs, energy arbitrage, you are connected to the grid and can buy/sell energy, and the provision of spinning reserves, not only from our engines, but also from other units, such as synchronous condensers. All of this can be managed by the microgrid controller, definitely delivering numerous benefits to the customer who decides to use it. Remember that our microgrid controller is not a standard solution. It is tailored to the client's needs for each particular case. This chart helps us understand when a microgrid controller is needed. If, for example, we have gas engines, diesel gensets, and turbines, a simple master controller is sufficient. But the moment we start integrating renewables, which by themselves vary so much depending on the conditions and must be monitored, at that point it is necessary to install a microgrid controller. To this we can add photovoltaics, wind, batteries. The idea is to have different types of assets and be able to control them optimally to minimize the system's operating costs. Here, through these QR codes, you can download two very good simulations. Business cases based on simulations we have done for two types of industries. For one, it was the hospitality industry, and for the other, the food and beverage industry. The hospitality example is interesting as it has no grid connection, unlike the food and beverage one which is connected to the grid. The good thing about this is that it can show you how using our microgrid controller can reduce the overall cost of energy and can deliver a fairly quick return on investment. Both documents can be obtained with these QR codes you see on the screen. And then we talk a little about the containerized solutions. What examples do we have? A first example, and one that many of you may have heard of, is Sky Global Partners. Here we sold 920 units that have been used for selling energy, basically. These were designed for continuous operation. They have also been used to sell during peaks when energy prices have been very, very high, especially in difficult winter periods. For example, in this case, we are talking about a total of 51.4 megawatts with an electrical efficiency of 47%, and this particular plant has been operating since 2016. Another example is AMG Energy Solutions, also in the United States, in Bradford. Here we are talking about generation mostly during peak hours. This is more what we would call a peaking plant, around 5,000 hours a year. This is an example where our containerized solutions can be used and, depending on the size of the site, you can even increase the number of engines depending on the gas, of course, that you can supply in a single location. This plant has 624 engines, providing a total of 21 megawatts at 44.7% efficiency. It's been in operation since 2019. This particular case has very good start and stop capability, quite flexible, because, as we said, they are used for selling when the price is at its highest or best. Another example of peakers is Forza Energy in Liverpool in the United Kingdom. This is a plant where we have different engines. The 616 and 624 engines deliver 20.7 megawatts with 45. You can see that the efficiency changes because it depends a lot on both the type of engine being used and the engine version. In this case, the engines were designed for confined spaces. That's why here you can see on the right the type of construction where the engines were installed. It's a good example when you want to save as much space as possible. This electricity is supplied solely for national consumption and, once again, for peak demand. Then we have a very good example in Gundremmingen in Germany. We are using our hydrogen-ready engines. This is a great example of combining engines with different ratings. This set has 26 624s and 2 620s. Why the 620s? They are, for example, engines that have ultra-fast or very fast start capability in under 30 seconds, which is a requirement of the grid operator to provide certain services that are very well paid. By adding, for example, engines that can deliver power or connect to the grid in 30 seconds, they can opt for this type of service and obviously make much more money. In this case, we are talking about a total of 123.6 megawatts with an efficiency reaching 46.8%. This plant is still under construction, but it is one of the plants we have delivered with our hydrogen-ready engines. These engines can be converted to run on 100% hydrogen, as I mentioned before, and for now they can operate on blends of up to 25% hydrogen with natural gas. Then, We have another example in Germany. This one is at a BMW factory, where the engines are used both for heat and for energy production. We're looking at types 616 and 620 with 20.1 electrical and 18.23 thermal megawatts, using both boost system efficiency to 87.8%. This plant added engines over time, explaining its different start dates between 2009 and 2011, 2012 and 2016, and it has been operating for years. In fact, here we also have black start capability. This is a plant whose commissioning is starting. This is one of the largest plants built in England. This is Tilbury in the United Kingdom. It is a plant that will have a total combined capacity of 600 megawatts between engines and batteries. And the idea of this plant is to sell energy when prices are at their peak. The United Kingdom is actually quite famous at the moment for the type of services it has created so that more and more companies want to build this type of plant. We are talking about 95 type 624 engines with a total power of 450 megawatts and an efficiency reaching 45.4%. And here we come to the end. Perhaps the takeaway should be that the technical capabilities of Jenbacher generator sets can help you a great deal when you want to support the grid and improve system stability. This can help you interconnect and also sell projects using our microgrid solutions, as our microgrid controller can be used with our engines. And the good thing about it is that it will be tailored case by case to what you need. Finally, the real cases. Notice there are many cases. We have been selling for many years and building plans with our customers. And you can see that depending on your needs, we can deliver the right solution. Thank you very much, and that's all from us. Here in this QR code, you can get a grid stability white paper. It's a white paper that I prepared, and it contains more detailed information than what we presented to you. Thank you very much.
Thank you, Free, for your presentation. We have been actively distributing the white paper. I inform you that on our site it is, in a way, well known, and I'm bringing you up to date. You know the Puerto Rico case well. You've become an expert. And it's not just happening there. I think we are seeing the same thing in the Dominican Republic. They're the two markets we serve and know well, and it's the same situation. I would say that in Central America, it's the same everywhere because the way in which electrical distribution networks are evolving requires this type of plant. I inform you that yesterday we submitted an expression of interest for a large tender being held in Puerto Rico to award 3,000 megawatts of baseload. We are not bidding for baseload. Rather, we are leveraging those expressions of interest to propose this type of plant that we know will be very necessary to stabilize a network as complex as Puerto Rico's because it has a generation fleet that is, let's not say compromised, but it is old and being renewed. Renewables are being incorporated at great speed. The network is also growing. In short, as we say, when you press down here, it pops up over there. And this fits perfectly with what is needed here. And I really appreciate the value chain this creates because we start with generation, but then comes the microgrid controller and my plan, which are very powerful and useful tools for managing this type of REV. So, Freddy, I thank you again. And with this, I'm going to volunteer you. If anyone has any questions, they should ask us, me, you, whoever. But I know that you like it. I know you're available. So I'll say it again. Thanks again, Freddy. So, well, we're going to distribute this to share it with as many people as may find it useful to learn. Very.